Hey there, it's Mixi91 and part 3 of Game Boy and Game Boy Color hacking tutorials using Pokemon Silver ROM as examples. And this time I'm going to talk to you more about ROM and also another type of memory called RAM. And for starting out, I'm going to open this Data Crystal site. datacrystal.romhacking.net wiki main page. And this is a site for hosting data for ROM hacking for several games. So the structures and how the games work and that kind of stuff. So here you can find a category of Game Boy and Game Boy Color games, and you can see that several Pokemon games are hosted here too. So let's open Gold and Silver category. And this is not really a place for tools. They can be found elsewhere and that kind of stuff. But the interesting thing we've got here are ROM and RAM Map. Very useful documents, both of them. So let's open one. And as you can see, this is an article called ROM Map for Pokemon Gold and Silver. And it's used to document how the ROM data works. So we've got a lot of stuff documented here, most found by Coolboyman. But I, as for myself, have added a bit to items too in the past. The smart data, actually. I don't think I've done anything else with it, but this is mostly by Coolboyman, the whole thing. And I don't think I have much to say about this really. But if you for example wanted to change the sprite shown in the intro, you would just go to this offset, change that bit byte to something else. It's the trainer group byte, and trainer group byte which relies on the pointer list order of trainers. So for instance, like I said in the last part, those what were they? Evolutions, moves and data had a pointer table, and so have trainers. So there's a pointer table to all trainer data, and this is just, well, let's just check it out. So it's in offset 5 FC2. And you can find 0A there. So Oak's trainer group 0A. This pretty much says that, and there's nothing more to it really. And there are lots of other stuff here as well. You can change the palettes and something about the items. You can actually use Mateo's item editor for editing items properly, so you don't really have to do much about this. Or actually, it doesn't allow you to change the coding behind how items work. So, for instance, how much health potion gives you. So, with it, this is useful. And you can change the flying map, wild Pokemon data, and here we have pointers to trainer battles. So for instance here, Oak's pointer is the 08 pointer in this list starting at 3993E. Pokedex. well, you can figure it out. Here we have uh, uh, stuff related to map headers. So this list here is pretty useful, although I don't think you need it that much, but because you can just use Jodo map to see where the map headers are located, but here are the pointers for them. And you can see that there's a little bit of blank data in the end of the ROM bank for adding new stuff if wanted to. Just like we added that, was it Starmie's? Probably Starmie's evolution and moveset data in the blank space in the end of the ROM bank. So here we have a little bit of blank space as well. And there are the map datas. I don't think this list is that useful really. And here we have a ROM bank with blank data in it. So this ROM bank is not used in the game. So you could store anything you wanted in this ROM bank. Well, yeah. You of course need some type of pointer for telling to read data from this ROM bank, because pointers, 2-bit pointers can only point in the same ROM bank, like I said in the previous part. But that is certainly possible, and not difficult either. Here we've got Overworld Sprites. So there's a program called Tile Layer Editor, and you could just use Tile Layer Pro or Tile Molester for editing them. So you can Google one of those tools and edit the Overworld Sprites with it. Some more maps. And here we've got musics. So here we have a pointer table to music datas, and they are located in this ROM area normally, but you can move them into another ROM banks as well if you want to. And here we have events and where they are stored in the game. Interesting thing here that we have a script of unused end event in 109428. So once you get the hang of scripting, you can well call script data from this offset and see what happens. And these are all event data and where they're located. And here we have global text. This seems to be unused ROM bank as well. And here is general text data in these 3 ROM banks, like what happens in the Poke Center. And although I don't think that is in here actually, but it was probably in this ROM bank if I'm right. Another global text ROM bank. And well, generally when you have to look for some text data, you don't go to the general text ROM banks and look for it there. You just type it in hexeditor's search function, the wanted text data, and search for it that way. Pokedex Text. And here we have item names, types of trainer names, Pokemon names, moves names, and all of these are probably found with a 3-byte pointer. So we have a pointer, and additionally we have a ROM bank to tell where to look for the data. So in this case, the pointer that splits this offset is 0040, because this is the start of the ROM bank. 00 here, and we got 40 leading to the first 00. And for this one, we, for instance, have our pointer as 55, 49, 56. What? I don't think this is correct. No, it can't be, because this is 1 byte ahead of this one. So there is some misdocumentation here of the offsets. But yeah, you can probably find them in this ROM back anyway. Pointers to move explanations, item explanations. And we've got lots of blank data in the end of the ROM, where pretty much everything or anything can be written to. And here we got documentation on different music bytes and what songs they refer to. And data maps. So here we have some maps that are not used in the game. If you want to check them out, you can use a map editor for checking them out. And here we have also documentation on how the map is sized in X and U size. But this is pretty much about this one. So keep this side in mind, and especially the ROM map. And last, we've got another document here called ROM Map. And I'll just show this first, and then I explain what it is actually for. So now here you shouldn't mustn't confuse these with the ROM map offsets, because if you look like D1FF, you could think that is in offset 0x D1FF in the ROM data, but this is not about ROM data at all. So here, when we open the ROM with the hex editor, we can modify the in-game data with this one. So you all the whole coding behind the game is the ROM. The ROM contains everything we need. But apart from it, we need another type of memory for storing data. So, and that memory here is ROM. So ROM is used for ROM stores all the in-game data in it. And how it works, that we've got this is how it works out. So we've got a processor. We've got RAM memory and ROM memory. And processor is connected to both of these. How could I say it better? This is how it works out. So basically, we have a processor that's used to look for data inside the ROM, and it can transfer that data in ROM memory. And from ROM you can it actually goes like this. So from ROM memory you can from ROM memory you can transfer data to processor to use that data, and you can store that data in ROM memory. So this one here contains the whole coding of the game, and the processor uses that coding for executing code. So it executes code written in the ROM, and what has to be stored somewhere is stored in RAM. And what is this that has to be stored? For instance, here we have map data. It's stored in a RAM address C700 to CAFF. So when you are on a map, or when you enter a map, the map data, or let's go back to ROM Map first. This is kind of complicated at first, but you'll get used to it. So for instance, we have map data of road 32 starting at A8000, and now a processor, when this map is loaded, a processor looks for the map data inside ROM, so in this offset, and it stores the map data in RAM starting at offset C700. As you can see, we have quite a bit of space here. We have all in all we have CAFF minus C700 3FF, or we forgot actually 400 hexadecimal bytes, because this is the first, because in C700 we've got the first byte, and C701 we've got the second byte. So in CAFF we got the 400 byte. But that's not very important whether it's 3FF or 400. But still, we have 400 hexadecimal bytes for map data that is loaded in this RAM address. And here you can see that the size of the map is A81C1 minus A8000, and that is 1C1 bytes. And that's not as large as 400. 400 is bigger value than 1C1. And that 400 is the maximum size of a map that can be loaded in RAM, because this RAM area is reserved for map data. So you can put up a map that would be bigger than that 400 bytes. And here road 32 is only 1C1 bytes, so that's okay. That can be loaded into RAM. The processor looks for data inside ROM and stores the data in RAM for usage. Because if we didn't have this ROM, we couldn't be storing anything anywhere. And it happens to be so we can't use ROM memory for writing operations, and we can't, how can I say it? I don't really know how to explain this much better than I have already, but we need another type of memory called RAM, which is read access memory, and this here is read only memory, so we can only read from it. And this is read and access, so we can read and access that memory. And the memory has to be stored in RAM that has to be used, or the memory that is used has to be stored in RAM. That's how it works out, mostly. So we have to look for data in ROM and store it in RAM. So as you can see, for instance, the wild Pokemon number you encounter is stored in ROM address DOED. And for instance, because, well, if it wasn't stored there, the game would have to guess what the wild Pokemon you're fighting against is every time. It has to be accessed during the battle. And so when we look for it inside ROM, we have to store it somewhere for later usage. And this is the ROM address where we store it. Or this was the number actually, and the level is stored in DOFC. And we've got, for instance, your XU position on a map stored in ROM, because if that wasn't, and you, for instance, entered the menu during when you're walking and you enter the menu, come back from the menu to the gameplay, the game wouldn't know where you are if it wasn't stored anywhere in ROM. And here we have it stored, so it knows the position where you are. In the beginning of the game, you can name the main player, and it has to be stored in ROM, because if it wasn't, it wouldn't know the name of the player. So ROM is only used for reading memory, and RAM is used for writing and storing memory data. That's how it goes. Your items in bag are stored in ROM, the badges you collect, all of this kind of stuff is stored in ROM. The save memory, when you save the game, it's stored all in ROM. Flags are stored in ROM, and these are used for telling the game whether certain events have been activated or not activated. For instance, when you fight a trainer, you can't battle the same trainer again if it was battled again. If you battle a trainer and win the battle, something is written in the ROM for telling that you can't battle that trainer again. It's stored in here. Precisely, it's stored in this ROM region. D7, B7 to D8, B6. All the Pokemon box settings are in ROM. The party you have at the time, the DV values, ID numbers, moves, levels, OP max HP, max HP, attack, defense, all this kind of stuff. Their names, original trainer, what Pokemon you have seen in the Pokedex or own their daycare Pokemon, because if those wasn't stored in ROM, the game wouldn't know whether you have a Pokemon in daycare, what the Pokemon is, have you received egg, all that kind of stuff. It's all stored in there. Opponent trainer, its Pokemon has to be loaded in ROM when the battle starts. If the opponent only had one Pokemon, he couldn't switch it, so that wouldn't be a problem, because the same Pokemon is the field all the time. But because he can switch the Pokemon and bring the one back again, the first Pokemon has to be loaded ROM as well. And this is how RAM memory works. Okay, I took a small recording break, and that's pretty much because I tried to do this following part already before, but I kinda messed up because I wasn't ready for this part coming up, and I tried to do better this time, but it won't be easy, because the following stuff is going to be kind of complicated, and it has to do about tools we have here with Visual Boy Advance. So we've got tools like Map Viewer, Memory Viewer, OAM Viewer, Palette Viewer, and Tile Viewer. And here from if you open the Memory Viewer, you will see this this thing opening up, and yeah, that ought to do it. For some reason my mouse is flashing like this, but let's not let that interrupt us. But yeah, with Memory Viewer, you can check what parts of ROM and RAM are currently accessible. So, like I said, processor can read data inside ROM and store that data in RAM. But it can also read from RAM. Yeah, processor can read from RAM, but it can't write anything here. It can only read from here, and here it can read and write here. Read and access, read only. And currently, or all the time, we can access these parts. So from ROM, we can read ROM data starting at the beginning of the ROM. So you can see here in the beginning of the ROM, we have these bytes F3, C3, 0001, 20, C9, FF, D5, F5, F16. The part accessible by Memory Viewer, it's totally the same as written in the beginning of the ROM data. And this is because read-only memory, or ROM, it works so that we can all the time read data from the first ROM bank, ROM bank 0. ROM bank 0 starts at 0x4000, which is 0000. This is the first ROM bank, starts at the beginning of the ROM, and it ends at 3FFF here. And so here we have also the first ROM bank ending right here, 14C9, 13EO. This thing here. So this is not copied or written anywhere. We can just, but we can use Memory Viewer for how to say it. We can read from the first ROM bank all the time. It happens to work so. This first ROM bank is accessible all the time. And this thing here, starting at 4000, it's probably not the same as we've got here in 4000. No, it's not. We have 29.6b C4, 9F, 91 CF A4. But this is because this here, it's a variable ROM bank. It can be any ROM bank besides ROM bank 0 that is accessible all the time. So this can be ROM bank 1, which we have here. It can be ROM bank 2, which starts 8000. ROM bank 3 at C000, or it can also be like this ROM bank here at 11Z000. It can be any ROM bank besides the first ROM bank. And because ROM is read-only, we can read data from this ROM bank. For experimenting, let's just check what the ROM bank this is. So we can use search engine to find this data, 991 CFA4, 91 CFA4. We have CF and B7, this should be enough. String not found. Probably wrote something wrong. Or did I? No. Currently we're probably accessing this ROM bank at 24,000. As you can see, it's exactly the same. The same data written here as happens to be accessed at this current moment in the game. So when we have this menu opened, we can access this ROM bank at 24,000 and the first ROM bank at offset 0. And then there is RAM memory. So all in all, we can access 8,000 bytes at a time from the ROM. So we can access the first ROM bank starting at offset 0, ending at offset 3FFF. It's the first ROM bank, and then we can access a variable ROM bank, which happens to be in the ROM. First ROM bank is in 4000, so the variable ROM bank starts at the ROM bank number multiplied by 4000. And this thing here is, for instance, ROM bank 24,000 divided by 4000, which happens to be ROM bank 9. And there we go. And that's not the result of the calculation is not 6 because we're dealing with hexadecimal, not decimal system. Of course. So yeah. At the current moment we can access these two ROM banks. First ROM bank and ROM bank 9, which is here. Then we can also access parts of the RAM memory. We have VRAM, SRAM, RAM, WRAM, IO. And this would be high RAM. Higher parts of the RAM memory. And here VRAM, it's called a video RAM memory. As you can see, the first tile is written to 8000. The next is 8010. And so on. For instance, the letters, they are also part of VRAM. So this is it's probably English to say, to think about it, abbreviation. That's probably the word I'm looking for. So yeah, VRAM is the abbreviation for video RAM. And we have, for instance, the font loaded in video RAM. This would be written in 8000 and 800 in RAM memory. So if we, for instance, do this, now A has been changed into nothing at all. 00 stands for nothing to be written in that, or the graphic being nothing at all. So now we disabled A, and you can see the effect in the game. We don't have A here anymore. And we can, we can use the video RAM viewer to change what's written in the video RAM memory. And it starts here at 8000 and ends at 997 FF. Or this part of it. Yeah. This part of it ends here in 97 FF. I'm not actually quite sure how this works out, that we have 2 video RAM banks. So don't ask me about it more. You can ask or find out for yourselves what's it about. But we have it's probably because of there being 2 layers in Game Boy that we can use. The first layer would be video RAM bank 1, or video RAM bank 0, and the second layer would be video RAM bank 1. And after after 97FF, we have the map data that is also loaded in video RAM, starting at 9800, and the map data ends at or the first part of the map data tends to 9B FF, and then we have some second part of the map data that ends at 9F FF. And for instance, in this new game continue screen, this map data is not used much at all. And like I was talking about, the current map data that is loaded right here, this has nothing to do about this map we have here. So this is like the graphics map that's used at the time. What is written in the screen as we see it? This is, this is the pretty much this is the background of the screen we have there. So for instance, I don't think people events are written in this map viewer, but instead we have the current screen written in the map viewer. What we can see at the moment in the game, that's stored here, starting at 9800, ending at 9FFF. Then we have the next part of the region. That is the save ROM area, and I'm not quite sure how this works out either. We apparently have more than one save ROM bank, just like we had more than one video ROM bank. But that's not important as of now. And the save ROM ends before C000. Then we have another part of RAM starting at C000 and ending at DEFF. C000 to DEFF. And this is the part of RAM where pretty much all the data that the processor looks for is stored. As you can see here, all of these addresses, they start either with C or D. Or we have the stored Pokemon they are in save RAM banks. But apart from them, we have pretty much everything in these. In the array starting at COOO, ending at DEFF. So yeah, if we for example start out and go to that address D1A1, set automatic update on. You can see that we were already given an ID number. Our current ID number is 1B8E, standing for probably has it written in the game, it's 07054. Let's just check it out. Yeah, like you saw, before or after clicking new game in the menu, some background code was executed for putting up that screen for where we wake up. Or let's just go through that again. As you can see now, we have nothing D181 because the game just started. Nothing is saved, nothing is loaded, so we have nothing in there. But now with that we click new game, now we already have an ID number. Because it was somehow randomized, because you get a random number, probably not totally random, possibly yes, I don't know how it works out, but still a somewhat random number that is written in this ROM address. And you can modify that later on with the memory viewer if you want to. That's not hard. You should know how to do that, because you can also modify data with a hex editor. This is no way different. And like I said, DEFF is the address where the work RAM memory, or the work RAM memory starts at COOO and ends at DEFF, and this is for pretty much only for Pokemon Gold, Silver, and Crystal, so it can be totally different for other games. But for these ones, it's here. And then we have, starting at EOOO, we have a thing called Echo RAM, and that is used for, well, I don't know how that works out, but that is something you should not even deal with. It's somewhat a copy of what's written in the work RAM, starting at COOO, ending at DEFF. We have a copy of that RAM here, or somewhat a copy of it. And after it, we have some register RAM, probably also something to do with, but this is OAM. Palettes are stored somewhere in work RAM, starting at COOO. Tiles were in video RAM, along with the current screen data that can be viewed with the map viewer. And here, starting at FF00, where the echo RAM ends. Echo RAM ends here. We have the higher parts of the RAM memory. And these are also something you don't have to worry about for a long time. I personally haven't done I haven't done really anything about it. Only a few codes that use them, but you can do quite a lot without even knowing how it works out, so don't worry about it. But the interesting things there surely are knowing how workram works and how to use this information here for changing several things about it. You can choose your own sprite and the clothes. This stands for the palette of the main player by modifying these RAM addresses. And it even happens to be so that when the game is saved, these are also saved in the save RAM. So when you load the game, your clothes are exactly the same, or the palette of the main player is exactly the same that you left it as before saving. So that's quite nice, I think. And for now, I don't think I have much more to be said about this. So, well, let's just check it out quickly, what I had in mind. Yeah. If you want to modify the level of the first Pokemon, well, you open the cheat list, add a Gameshark code here, and here you put the level of that Pokemon. For instance, 05 stands for its level. And this thing here is a permanent change, so once you've done it, it cannot be undone anymore. Or how to say it? If you put it on and not disable the code, now it's enabled. If you don't disable it, the first Pokemon will stay being at level 5 no matter what happens. So you can modify. This here is used for modifying RAM memory. And guess what? What kind of, or where do we modify the RAM? Well, we have D8 here and 49 here. So if you go to Pokemon 1 settings, you can see that the level is in D8 49. So this simply 01 is telling something, I don't know what it's for. Then we have byte to be written to and the RAM address rotated around. Just like before, just like with anything else, you have to write everything in another type of an order. So instead of D8 49, you write 49 DE DA, just like with ROM pointers. This points to ROM pretty much. It points to ROM address D8 49 with 49 DA, and 05 is the level or the byte to be written to that RAM address. And if this code is enabled, that change is permanent. So it will stay at level 5 no matter what. So yeah, this is how Gameshark codes work. You can easily write your own, or do pretty much anything you want with these codes. Here are so-called walk-through walls codes, which only thing they do is write data in these 4 RAM addresses, and they happen to write 0A there in each slot. And that just is for telling that you can walk into this direction. Now the first code is probably for you can walk down, you can walk up, you can walk left, you can walk right. And this is walk through walls code. No random battles. D2 OB is written to 00. D2 OB. Wild Pokemon battles enabled. They are not enabled. These I was actually expecting they to be doing something about repelling instead. So if you, for instance, write 05 or put code like 0105 EB D9, that is making a permanent change that you have 5 steps left repelled. But yeah, that's pretty much about it for now. So you should know how to write your own Gameshark codes, know more about RAM memory, how it works out, and that kind of stuff. And next time I'll probably explain more about the event structures, and we'll get to simple scripting then, because I think I have done everything or explained everything up to then that you need to know. So that shouldn't be a piece of cake, but still something that you can, well, you should be able to get into that as well after knowing all about this.